The homework problem you're going to be doing this week is a little different from the ones you've done before. We're going to be completing a part of a program. We're going to be doing a percolation class, which is going to use one of the union find structures that we talked about in lecture. So you're going to finish this class. It's unusual in several respects. One is that you'll note that there is no main method here. That's because I'm going to give you some other classes to go with it. So you're going to find this class inside of the perc folder inside of algs 1.5. And you'll see 4 different classes there. There's the percolation class itself. Then there's an interactive percolation visualizer, a non-interactive visualizer, and a statistics class. So these 3 classes all contain main programs that will use your percolation class. Let's just look at how one of them works out of the box. This is the interactive percolation visualizer, and you'll see what it does here when I run it. It's going to pop up a little window, and I can then click. I'm clicking with my mouse, or you can just hold the mouse down. And you'll see 2 things are happening. One is that I'm getting numbers on the console telling me which position on the screen I'm tapping. And I'm also getting a visualization of that tapping. So if I tap the same square over and over again, of course, nothing happens. But when I tap new squares, something happens. Anyway, this is what you're going to have out of the box. And your job is to make this file do what it's supposed to do. So what is it supposed to do? In order to explain that, I need to give you some background. So I'm going to be using some of these slides from the textbook to do that. What we're looking at here is an application of union find. There's lots of applications of this union find algorithm. The one in particular that we're looking at is going to be a percolation problem. So what does that mean? The idea here is that I have some sort of solid that's got holes in it. And let's say there's some liquid, or you can think about like water at the top of this solid. And the question is, how many holes do I need in that solid before the water will sort of drip through to the bottom? So you can think of this like a coffee filter or whatever you like. It's some sort of semi-permeable surface that has a liquid on top that we're trying to get through. And the idea here is that we're going to have some blocked sites. Those are going to be visualized in black, and some open sites, which are visualized in white. And we'll ask this question of whether or not we percolate through this surface. So can something go from the top down to the bottom by going through a connected path of open sites? And you can see here on the left, this percolates. On the right, it does not. And we're going to be doing this for various sizes. And for whatever reason, the authors of the textbook have chosen in here not to be the size of the entire grid, but simply the size of one side. So in general, the problem size here is the square of this number. So this is a 64 cell grid. To make the visualization a little bit more compelling, we're going to add one more element, which is this notion of full cell. So when a cell is open, it can be filled with the liquid from above. So here we're visualizing these in blue. And note that the water goes strictly down, or the liquid goes strictly down. So if I manage to get water through here to the bottom, it doesn't go back up on the other side. So this is gravity, if you like, pulling things down. And here you can see very clearly in the visualization how things percolate through this path. And here, of course, they can't. So this is an aid to visualization to help us see when the system is percolating and how. We can use the concept of percolation to model lots of things, not just liquids going through semi-porous substances, but also electricity conducting through a system, or even a message communicating through a group of people. The question we're interested in here is a sort of stochastic question or a random question. We're going to be interested in knowing what's the number of sites I need to randomly open up, or how many random connections do there need to be before the system is going to percolate from top to bottom. So we're going to open up sites with some probability, P, and that means that they'll be blocked with probability 1 minus P. And you can look at the kind of things that happen for various values of P. So if P is really small, or it's about, in this case, 0.4, if you run this simulation over and over and over again, you'll see that it's extremely unlikely that the system will percolate. It's almost impossible. You can get lucky, but it's very, very unlikely. If P is high, in other words, if I open up 80% of the sites, then it's almost assuredly going to percolate. So the question here is, where's the happy medium? Where's the point where it sort of, jumps the shark? Where is the point where I go from almost impossible to percolate to inevitably going to percolate? And what we'll look at is the 50% point. So when do I have a 50% probability that the system percolates after opening up P% random sites? And it turns out that there is a number here, and it's going to be right around 0.6. And this is kind of a shocking fact of mathematics. There's no known solution to this problem analytically, but we do have a solution to the problem using experiments. So what we do is we just run these kind of percolation problems over and over and over and over and over again. And you note, if you map the probability of percolation, then it's actually got an extremely sharp curve right at some number P star. So there's this P star, which is the probability at which, if you open up fewer than that percentage of sites, you're almost impossible that you'll percolate. If you open up more than that percentage of sites, it's almost inevitable that you'll percolate. And so the question is, what is this? And the way we can find out is by doing a kind of random simulation. So what we're going to do is initialize a grid with everything blocked. Then we're going to randomly open up sites and see how many sites we have to open in order to get the thing to percolate. So here's a particular simulation running, and you can see here that the sites that are connected to the top and open are visualized in blue. The sites that are open but not connected to the type are visualized in white. And you can say, oh, look, well, what happened? We opened up one little site there and suddenly it percolated. So this is the problem you're going to be working on. The question here is how to model such a system. We've got to have some sort of grid, and we've got to be able to efficiently open up two sites, and we have to also be able to efficiently find out whether anything on the top is connected to anything on the bottom. Well, I can obviously use something like an array to indicate which sites are open and which sites are closed. And in the percolation file that I'm giving you, I've already actually given you that part of the solution. So you'll see here in the file that you've got, I'm giving you an open array, and the number in, that's the size of one side of this in by in square. And in order to model the open and closed sites, we need in squared location. So I'm going to do that with a Boolean array of size in squared. And now what we're going to do is model each element of that square using numbers. So I have an I and a j, and I will indicate the row. So we multiply I by n, and then just add j to get to a particular square. You can see already here I can answer one interesting question, which is the question of whether or not a site has been opened. So in order to open a site, I set it to true. In order to tell whether or not it's open, I simply return the Boolean that's stored. And this is what's being used by the interactive visualizer to cause these white squares to be drawn white. They're opened. So all the software is doing here is every time I click, it's calling the open method for the particular element, and you can see which ij combination printed out here. So I just opened up 0, 1. Now if I click here, it'll be 0, 0. If I click here, it's going to be 4. This is item 4, which is actually row 1, column 0. So this is a 4 by 4 grid. And so we go 0, 1, 2, 3, 4, 5, etc. So a click on this grid is a call to open. And every time it's drawn, the software calls the isOpen method for every element here in order to draw the picture. So that's great. I've got this nice grid, and I have this idea of using numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is for a 5 by 5 to represent whether or not something is open. And so it's pretty straightforward how to represent open and closed sites. But it's not obvious how to use this data structure to answer the question of whether or not this grid percolates. If you think about it, it's going to be a kind of complex algorithm. I need to start at any node at the top and see if I can follow some connected path down to the bottom. This is actually very similar to a maze exploration problem. And you'll look at this in data structures too, this kind of general idea of exploring a graph. But for our purposes, we don't actually care how we get from the top to the bottom. All we care is that they are connected. Oh, and that means we could use something like a union find structure to represent this. Well, let's think what a union find would look like in this case. We'd have 25 elements, and we could just number those 0 up to 24. And what does it mean then for our connectivity? Well, we'd say here that 0 and 1 are connected. Likewise, here we have 3 and 8 that are connected. And you can see the connectivity graph drawn here corresponding to this picture on the left. The numbers have been erased, but you get the idea. So this corner here corresponds to this corner here, and so on and so forth. Note that cell number 17 here is not actually connected to anything. So even though it is open, it's not connected. Likewise, its neighbor here, cell number 11, is also open, but not connected to anything. So this is a representation of the structure. And now it would be relatively straightforward to calculate, given this, does it percolate? What we want to know is if there's any connection from the top row to the bottom row. A simple way to calculate this is just to go through each element of the top row and ask for each element of the bottom row, are they connected? Note that that will result in n squared calls, where n is again the length of a single row. That's fine, it's not going to be dreadful, but we could actually do better if we're only using this union find structure in order to determine whether or not this percolates. Then I could actually just join all of the elements of the top row together, join all of the elements of the bottom row together, and then all I need to do is ask whether the 0th element is connected to the n square minus 1th element. And this is what your book calls a virtual top site and a virtual bottom site. You don't actually need another node. You can just connect all of the top row together, connect all of the bottom row together. And now I can just do one call to the connected method to ask, is the 0, 0 element connected to the n squared minus 1 element? And that's all you need. The way the authors of the textbook have set up this problem is that the water on top of this virtual solid only percolates down. It doesn't go back up. And that means that we have a separate question we're interested in, which is whether or not a site is connected to the top. And this is an independent question. Here you can see the elements painted in blue that are connected to the top. And to do this, I actually have a slightly different criteria that I want to use. So here I don't want to connect all the elements on the bottom row. I just want to connect all the elements on the top. So this sort of says that what I need is a separate union find structure to answer this question. So the solution I'm proposing is that you're going to use two union fine structures, one to model the question of whether or not we percolate from top to bottom, and the second to simply model whether or not something is connected to the top. The difference between these is just how they're initialized. In the case of answering the percolation question, we're going to want to initialize this to connect all of the elements of the top row and all of the elements of the bottom row. And for answering the question of whether or not something is full, we're just going to want to connect the top row. We'll leave the bottom row empty. When you implement this, you'll end up with something along these lines. So you'll have a union fine structure to represent whether or not something's full, another union fine structure to represent whether or not something percolates, and you'll need to initialize those two fields when you get the value in. So for a percolation of size n, we're going to want to create the two union fine structures of size n squared. What's left to do is to initialize these two structures to connect them as we just described. We also are going to need to fix the open method. As well, we'll need to implement isFull and percolates. But these two methods are going to be very, very simple. This is going to be simply returning whether or not something is open and is connected to the top. That's how we do full. And then here we're just going to implement whether or not something is connected from top to bottom. And we can answer each of these questions with a single call to the connected method of the corresponding union fine structure. The biggest challenge in this homework assignment is how to implement the open method, because the open method is going to need to modify both of these union fine structures in order to update the connectivity as we open up cells. Let's think about how we do that for a cell somewhere in the middle of the graph. If we open up the site here, right smack in the middle of this particular graph, what are we going to do? Well, we'll look up and see that there's a closed site there, so there's no work to do. However, note that there's open sites to the left, to the right, and to the bottom. And so what we're going to want to do is connect this new open site to all of those three neighbors. Now, I don't need a loop to do this. I need 4 if statements. So if I look up and there's someone above me and they're open, connect. If there's someone to the left, then connect. If there's someone to the right that's open, connect. If there's someone down that's open, connect. I'm a child of the 70s, so every time I think of this kind of looking around, I think of the TV show called The Brady Bunch, or perhaps the Hollywood Squares. In any case, that's what we need to do. We need to do 4 different looks. Note that we're not connecting diagonally here. We're just connecting up, down, left, right. Once you've finished your implementation, you can check it out and you can actually run the statistics file to see what the actual P star is for your particular simulation. And you'll find that it's around 0.59. So again, this is a constant that we don't know analytically, but we do know it via simulation. So let's look at what you are going to expect as your solution is finished. And to do that, I'm going to look at my solution and how it works in the interactive visualizer and these other classes. In the interactive visualizer, what you'll get is a screen up, and when you have it working, as you click around, you'll get the white squares, obviously, but when it's actually working, when you connect to the top, things will turn blue, and that's because these sites are full. So if I open up some more sites here, and you can just hold down the mouse to open, you might think of a couple of different paths that I have here. And now the question is, when I come up and I connect one of these paths to the top, what's going to happen is that all of these will become full and the thing will percolate. So you can see it's listing the number of open sites, it's saying whether or not it percolates, and you can tell which ones are open and which ones are full. So if I click right here, boom, all of these sites are now full. It does percolate. And you can see these other sites are open, but they're not full. And that's the idea of the interactive visualizer. So you can play around with it. It's kind of fun. There's also another program here, which is a non-interactive visualizer. And when you start this one, it's going to randomly open up sites. And you can just see this here. I've got, I think, a 10 by 10 grid, and it's going to randomly open up things. And you can see here it percolated when I hit 50. So this is a loop that will go until it percolates. If you don't have the correct code, it may be an infinite loop here. So you need to be careful. But let's try it again. And it's fun to watch this and just sort of see what kind of statistics you get. You can run it a few times. I got 62. And you can see both those are, it's an upper bound and a lower bound to the 0.59, which is what's experimentally what I'm expecting. And again, here I got about 54. So that's a stochastic stimulation or a Monte Carlo simulation. I love this idea of Monte Carlo. It's like I'm gambling. Anyway, all Monte Carlo simulation means is random. We're using random numbers to come up with a result. So that's the non-interactive visualizer giving us random data. If you want some non-random data, the authors of the textbook provided a bunch of files, and they do different things. So here's a snake, for example, and you just go down to your main method here, and you can uncomment a line. And this may take a while. It's a little picture that's going to present something to us. Let's watch it in action. This is the good part. Toward the end, we're going to almost get this snake, and then watch it as it completes here. We're going to connect one right at the bottom. So the last thing we did here was connect this little bottom square. So there's a simulation. You can watch your code execute that long snake. You can also see some other things. I don't read Chinese, so I'm not sure what this says, but hopefully it's not obscene. And there's other things here you can play around with. So I have given you in the Percolation folder these files. These are the text files. And as well, there are some images here which show you what they're supposed to look like. So you can see here, this is a heart. Then that's what the heart is supposed to look like. Finally, you can change the size of the random grid if you like by modifying line 128 in the file that I have here, which is just changing the number, which is the argument to the method. And you can see here I'm creating just a larger grid, and it will take a long time to fill in. The last file you have is a percolation statistics file. And what this is going to do is run your percolation, repeatedly opening sites until it percolates. And we're going to just measure that over and over and over again. When you run this on the percolation file that I've given you, you might actually get an infinite loop. I added a bound in here to line 17 to stop this thing after n-cubed tries. And so if you've got that in your code and you run this on the raw input, you'll see that what you get out is something like this. And what this is telling us is that the number of sites we opened is actually all of the sites. So we're getting a mean of 1.0. That means I opened all the sites. And in fact, the thing never percolated anyway. So that's sad. Let me show you what this should look like once you have your percolation class finished. When I ran the percolation statistics on my solution, you can see the results that I got. For about 20 million cells, it was taking more than a minute, but that's running 10 different simulations, so each one of those is about 10 seconds. The percentage of cells that needs to be open is almost exactly what I expect, 0.59, and you can see that's quite tight. And in terms of performance, I am getting linear rhythmic looking results. So it's not quite linear, a little bit worse, and that makes sense. I'm doubling the amount of cells I'm looking at, and each one of those queries is taking about logarithmic time. So in total, we're getting sort of a linear rhythmic kind of performance here as we increase the problem size.